time for attending this session today. My name is Deepthi Goguri. Thank you so much, DenverSQL user group, for giving me this wonderful opportunity to present for you user group today. It's an honor, and hopefully I will see you again in the future. Hopefully, if I get the acceptance. So in this session today, we are going to talk about the life cycle of a query in SQL Server. So this particular session is all about like what happens behind the scenes inside the SQL Server, like when you submit any query to SQL Server, before you see the results on your screen, what happens behind the scenes. So there is a lot of content to grab, so hopefully you like it. So let's get started. A little bit about me. I'm a database administrator with 7 years of experience in managing SQL Server and databases. I'm a Microsoft certified trainer and Microsoft certified solution expert. I did my master's in computer technology at Eastern Illinois University and a blog for dbanuggets.com. That's my website. And I'm really active on Twitter. So you can contact me on Twitter at dbanuggets. That's my user ID. And if you have any questions regarding this session, you have my email address there and my Twitter ID. Please don't hesitate to contact me. So in this particular session, what are we going to discuss today? We are going to start with the basics, the asset properties of a transaction, with a very simple example ensuring the asset properties. We are also going to see the different types of components we have in the memory architecture of SQL Server. But in this particular session, we are mainly focusing on the plan cache and the buffer pool, and how does these cache get managed inside the SQL Server. We are also going to see the life cycle of a query for the read as well as the write transactions. And we are also going to talk about the different types of components we have inside the SQL engine. That's the components of Relational Engine and the components of the storage engine. So internals, why should we care, right? Even without knowing the internals, we can just go ahead and do our regular jobs. But many DBAs and developers, they work with SQL Server on a daily basis, but they might not know exactly what happens when we submit any query to SQL Server. So knowing this information will help you in understanding how queries are processed at each stage inside the SQL engine. It will also help you in tracking down the performance issues very quickly and fix them efficiently. It will also build you the confidence while managing the database engine as well as the databases. It will also help you in convincing your coworkers or managers of why they have to take your ideas seriously, because now you know, by the end of this session, you will know what is really going on behind the scenes. So if in case you have to suggest something, then they have to listen to you because you know the stuff, right? And the last but not least is we work with SQL Server every day. So the more we know about the internals, the better we can understand how the SQL engine works behind the scenes. So let's go ahead and start with the basics, the asset properties. Every major relational engine, right? It can be SQL Server, Oracle, PostgreSQL, Sybase. All these major relational engine should satisfy the asset properties of transaction. So what is this asset? A stands for atomicity. Atomic meaning a single unit of work. A single transaction can contain one operation or it can contain multiple operations in it. Whenever you run a transaction, it should be either complete successfully or none of them. Let's take an example. Let's take an example of a stored procedure. Inside the stored procedure, we have an update statement as an insert statement in it. So whenever you execute the stored procedure, both of those operations should either complete successfully or none of them. For example, if the update succeeds and if the insert fails, then SQL Server should go ahead and roll back the entire transaction. That's atomicity. C stands for consistency. So the data inside the database should always be consistent before starting the transaction and after completing the transaction. Let's take an example. I wanted to run an update statement on a table, right? And while I'm doing that update, if something happens suddenly, like there is a power outage, and if we have to restart the SQL Server, once I restart the SQL Server, this particular uncommitted transaction should be completely rolled back, making the data in the consistent state. That's consistency. I stands for isolation. No matter how many concurrent transactions are happening at the same time, each and every individual transaction should be independent of each other and should not be interfering with any other transaction. Let's take an example. I wanted to insert bunch of records into a table, right? And while I do that insert, none of the other transactions which are running concurrently should be interfering with my transaction. That's isolation. D stands for durability. So once the transaction is successfully completed, and all the data that has already been made to the database should be permanent. Like let's take an example, like once the transaction has been successfully completed and once the data has been already made to the database, later if I have to restart the SQL server, that particular committed data inside the database should not be lost. That means there should not be any data loss. That's durability. So what components of the SQL engine will ensure this asset property? Atomicity is very easy to be ensured. It is taken care by the parse component inside the relational engine. Consistency is also very easy to be ensured. It is taken care by the parser and binder components inside the relational engine. Once the atomicity, isolation, and durability are ensured, consistency will automatically be ensured. Isolation is all about the locking mechanism. Like it is taken care by the lock manager inside the storage engine. Durability is the most toughest of all. It is taken care by the transaction log inside the storage engine. Let's go ahead and see a very simple example ensuring this asset properties of transaction. Let's take a simple bank transaction. For example, let's say I have a balance of $500, which have an ID of 1, account ID, and I would like to send $100 to my friend's account, which have an ID of 2. So this particular simple transaction has 2 operations in it. The first operation is to deduct $100 from my balance, which have the balance of $500. And the next operation is to credit $100 to my friend's account, right, which have an ID of 2. So I can do this simple transaction multiple ways, right? I can use online application to do it, or I can even use mobile phone application of my bank, right, on my mobile phone. In this particular example, let's take the mobile phone application. Once I begin the transaction on my mobile phone, behind the scenes, SQL Server will also begin the transaction. The first operation, it will go ahead and deduct $100 from my balance, which makes $400 in my balance. And the second operation is to credit $100 to my friend's account. But I suddenly see this on my screen. I am logged out of my mobile phone application and I suddenly see this alert saying, facility is temporarily unavailable, please try again later. Now, what has happened? I'm in between the transaction. I do not know if my $100 has been lost or if my friend has received $100. So I don't know what has happened. So I immediately called her and asked if she received any money, which she said she didn't. So I immediately called bank customer service guys very angrily to know what has happened. So they said there was a severe thunderstorm and some of their SQL server went down and they already restarted them. So if this particular transaction is ensuring the asset properties of transaction, what should happen once they restart the SQL server, right? Let's go ahead and see. So after they restarted the SQL server, that transaction, which is my transaction, which is in between, right? It is not completed yet. So that particular uncommitted transaction has been completely rolled back, making the data in the consistent state. This particular transaction is ensuring the asset property. Now how? Atomicity is ensured by rolling back the entire transaction. Consistency is ensured by reflecting $500 in my balance, which is the initial amount before starting the transaction. Isolation is also ensured. Like, did you observe when SQL Server went ahead and deducted $100 from my balance, which is the first operation, none of the other transactions are being interfered with my transaction. Durability is also ensured. I did not lose my money. My $100 is back into my account, which is reflecting correctly $500, which is the initial amount before starting the transaction. So that's how Each and every single transaction of all these relational engine should satisfy. Now let's go ahead and talk about the SQL Server memory architecture. SQL Server Engine is a Windows program which will use Windows APIs to allocate memory to the SQL Server. So there are different types of components we have inside the memory architecture of SQL Server. But in this particular session, we are mainly focusing on the plan cache and the buffer pool because they are the bigger components, right? But let's go ahead and see what other components also we have here. The first component, which is one of the bigger components, it's plan cache. It holds the store procedures, query plans, etc. The buffer pool, which is the biggest component of all, it holds the 8 KB data pages and the index pages in it. There are also other type of cache like log cache, token and perm user store cache. Now what this token and perm user store cache does is it will store the user permissions onto the objects. There is also other type of cache known as column store cache, which will store column store indexes in it. Now all these caches which you are seeing in the blue color are very special. Now why I say that they are very special? Because they have a backing mechanism in them. Because they have a backing mechanism in them, they can be easily expanded and shrinked when there is a memory pressure. Like let's say, like what is this backing mechanism, right? That I'm talking about. Let's take an example here, the plan cache. The store procedures which are stored inside the plan cache, the query text behind the store procedures are stored inside the system tables. That's the backing mechanism for it. Let's take the buffer pool. The data pages which are stored inside the buffer pool, they are saved as the database files inside the disk subsystem. Let's take the log cache. The log cache is stored as the transaction log inside the disk subsystem. And the column store indexes, which are stored inside the column store cache. These column store indexes are compressed and they are also stored inside the disk subsystem. Because they have these packing mechanisms in them, they can be easily expanded and shrinked when there is a memory pressure. But what about the fixed memory you are seeing in the green color? Fixed memory, it is known as fixed because it cannot be expanded and shrinked when there is a memory pressure. Now, what kind of things will be saved inside this fixed memory? The connections to the SQL Server, like, for example, the memory grant connections, which we use for the hashes and sorts for our queries, those kind of connections are stored inside the fixed memory. Now, this particular fixed memory cannot be shrinked and expanded when there is a memory pressure, right? So what if our queries are requesting for more and more memory grants, and what if this fixed memory gets full? In that case, fixed memory can't do anything. It can't expand it or shrink, right? So SQL Server, inside it, there will be now memory pressure within the SQL Server. And the SQL Server have an alert system in it. It will go ahead and request all these other caches, which you are seeing in the blue color, because they are the ones which can be easily expanded and shrinked, right? So SQL Server will go ahead and request these caches. Like let's take an example of plan cache here. It will go and request the plan cache to evict all the execution plans inside it such that it can get some memory for these memory grant connections. That's how the fixed memory gets managed. Let's go ahead and talk about SQL Server.exe overhead memory. As you know, the SQL Server.exe is an executable and many things will be running this executable, right? Like for example, the thread stacks. Even this will come under the memory architecture component. Now there is other type of component known as in-memory OLTP. In-memory OLTP is also fixed memory. It cannot be expanded and shrinked when there is a memory pressure. Now memory optimized tables get stored inside this memory. There should be some other process which should come and clean these tables such that it can have some more memory for the newer object to be stored inside it. That's just an overview of the memory architecture of the SQL Server. But let's go ahead and talk about how this plan cache and the buffer pool gets managed. Now, how the memory gets managed. right? Inside the SQL Server, there is something known as LRU algorithm, which is also known as least recently used algorithm. The hyphen K is for the complexity of the code. Now, what is this LRU? LRU meaning if something is staying inside the cache for the longer time, those kind of things will be discarded first. But what happens with the SQL Server? SQL Server will think this way. Like if there is an execution plan which got easily created with low amount of cost and the resources, and if it is not being used, those kind of execution plans will be discarded first. But if there is an execution plan which is complicated, right, it took so much of resources and cost to get created and to be saved inside the plan cache, those kind of execution plans will have longer time inside the plan cache. They will have more chances to stay. Let's talk about the plan cache, like how does it get managed? Now there are two processes which will manage the plan cache, the lazy writer and the ghost cleanup. Now let's go ahead and talk about how these processes works. The right side diagram which you are seeing is my plan cache, and we have 3 execution plans in it. It's really small. On each object we have inside the plan cache, we have 2 numbers at the bottom of each object. The left side number is known as complexity code value, and the right side number is known as complexity countdown value. Now, when the lazy writer gets kicked in every minute by the SQL Server automatically, lazy writer will go ahead and check if there are any least recently used execution plans. Here, in our example, none of them will be used. So the lazy writer will go ahead and decrement the complexity countdown value on each object it thinks it is not being used. It will just go ahead and decrement by 1. So here, it will go ahead and decrement the complexity countdown value for the plan 1 from 18 to 17, for the plan 2 from 9 to 8, and for the plan 3 from 2 to 1. And the lazy writer will go away. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. Here in our example, none of them will be used again. So it will go ahead and decrement the complexity countdown value for the plan 1 from 17 to 16, for the plan 2 from 8 to 7, and for the plan 3 from 1 to 0. And now, did you observe, like the plan 3 complexity countdown value for the plan 3 has turned to 0? That means the SQL Server should go ahead and evict this plan out of the cache, right? But that is not what it is going to happen. There is one more process which is known as ghost cleanup. It will be kicked by the SQL Server automatically every couple of minutes. Now, whenever it gets kicked in, it will go ahead and check if there are any execution plans with no countdown value. Once it finds them, it will go ahead and flag them as ghosted. That means these plans are still inside the plan cache, but they are in the half-life. Let's say there is a memory pressure tomorrow within the SQL Server, right? Then the ghost cleanup, it will go ahead and evict these ghosted execution plans out of the cache. But what if there is no memory pressure? Then SQL Server is still going to keep these execution plans inside the cache, such that there might be the other user who might come and use the same execution plan for his query later. That's how the ghost cleanup works. In the very next minute, the lazy writer will kick back in again to see if there are any least recently used execution plans. Here, plan 2 will be used now. So the lazy writer will go ahead and increment the complexity countdown value for the plan 2 from 7 to its original value, which is 9. That's how the plan cache, that's how the lazy writer and the ghost cleanup will work for the plan cache. Now let's go ahead and talk how buffer pool gets managed. As you know, the buffer pool will hold the 8 KB data pages and the index pages in it. Buffer pool has to manage 3 kinds of different structures: the clustered indexes, non-clustered indexes, and heap tables. Let's take an example. You wanted to run select star from a heap table. When you do that, you know what will happen. The buffer pool has to go ahead and grab all those data pages inside the buffer pool to do the operation, right? But which is very IO intensive because buffer pool has to go many trips to the disk subsystem to grab those data pages. But what if you put clustered index and non-clustered index on top of those top of the heap table? Now that the buffer pool has to go ahead and grab some of the pages into the buffer pool, it will help reduce the IO, right? These indexes will help reduce the IO as well as it will help speed up the query process. Now, how does the buffer pool gets managed? There is something known as checkpoint process, which will be kicked in by the SQL Server automatically every few minutes. Now, whenever it gets kicked in, it will go ahead and check if there are any dirty pages inside the buffer pool. Now, what are these dirty pages? Dirty pages are the data pages which are already modified inside the buffer pool, but they are not yet hardened them to the database file system. Now, whenever the checkpoint process kicked in, it will go ahead and push back all these dirty pages out of the buffer pool and push back and harden them onto the database file system. That's how the checkpoint process will manage the buffer pool. Now let's go ahead and talk some important things, right? This is a very important slide. How SQL Optimizer will choose the plan. You all wanted to know about this. As you know, the SQL Optimizer is a cost-based optimizer. It always wanted to choose good enough plan instead of the best plan. Now, what is the difference, right? The time and the cost is the difference. Let's take an example here. We have a very simple select statement here with a 4-table join statement. Let's say each table have a clustered index and 3 non-clustered index on the top of each object. Now, what if the optimizer have to go ahead and get that best plan instead of the good plan? What it have to do? First, the optimizer have to go ahead and analyze 72 different types of physical access methods per table. That means in this select statement, simple select statement, we have 4 tables, right? That means 72 times 4 physical access methods. Now, what are these physical access methods? The optimizer have to go ahead and analyze like whether it have to do the clustered index scan or non-clustered index seek, or whether it have to do any key lookups or not, those kind of physical access methods, 72 per table. On the top of it, optimizer have to go ahead and analyze 24 different types of logical join orders. Now, what are these logical join orders? Here in our example, we have a 4-table join statement, right? Let's say the join between A to B is filtering out around 50% of the records from the result set. And the join between B to C is filtering out around 80% of the records from the result set. In that case, the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C, front of the statement, and the join between A to B, back of it. Now, why the optimizer do that is because it wanted to grab the results as quickly as possible. Such kind of logical join orders, 24 it have to go ahead and analyze to get that best plan. And on the top of it, it have to go ahead and analyze so many transformation rules, at least some thousands of them. And out of analyzing all of them, it will grab approximately 26,000 possible plans. And out of those 26,000 possible plans, it have to choose that best plan. Sorry about that. So just imagine how much time and resource consuming it is for the optimizer to go ahead and analyze all these transformation rules and get that best plan for this very simple query. It will take so much of resources and time, and no user wanted to wait for such long time to get the results, right? That is the reason the optimizer, without going ahead and analyzing all these transformation rules, it will go ahead and analyze some of the transformation rules to get that good enough plan as quickly as possible. That's how the SQL optimizer works inside the SQL Server. Thank you, Kevin Klein, for loaning me this example. If I tell the same concept in a very simple way, let's take a query, right? An optimizer analyzed some of the optimization rules and thought execution plan A will be better in 3 milliseconds. And it thought execution plan B will be better in 3.5 milliseconds. But in order for the optimizer to know if the plan A is better or B is better, it have to go ahead and analyze at least for 5 minutes for analyzing all those transformation rules. The optimizer doesn't want to do that. It doesn't want to go to the third step. It will just go ahead and randomly choose the plan A or plan B randomly. That is the reason why the optimizer is so quick. Now let's go ahead and talk about the life cycle of a query. Before going into life cycle of a query, can I ask if you have any questions? Anyone, any questions?
I don't see any on the chat yet, so.
Sure, let's go ahead then. So if the life cycle of a query is divided into 3 different steps, then the first step contains the components parser, binder, simplification, and trivial plan. Now, all these components from the first step are very simple and very lightweight to the SQL Server. Like SQL Server doesn't need much metadata to process these components. All it needs is like query definition, table definition, very simple things. But when you come to the second step contains the components load metadata, join heuristics, and search phases. Now, all these components from the second step requires most of the metadata to process any query. Now, when you come to the third step contains the components access methods, transaction manager, and buffer manager. Now, when you compare the third step components with the first 2 step components, third step components are very IO intensive. Now, why I say that is because we have buffer manager component, which will have to go ahead and interact with the disk subsystem, right? Which is very IO intensive. Now, this is just an overview of what all components we have. So the first step components and the second step components will come under the relational engine, and the third step components will come under the storage engine. Now, this is just an overview. Now let's go ahead and see how a SQL Server select query runs behind the scenes when a user submits the query. First, let's talk about the select query, and then let's go for the write transaction, right? Here, a user wanted to send a select query to the SQL Server. No matter what kind of interface he is using, he might be using SQL Server Management Studio, Azure Data Studio, .NET Visual Studio, or even a third-party application. No matter what kind of interface he is using, he should first get the secure network connection to the SQL Server. Now, how does he get that? There is something known as SNI, which is also known as SQL Server Network Interface. Now, what the SQL Server Network Interface does is it will establish a secure network connection between the SQL Server as well as the client. So our client is our user here. So the SNI, it will use internet protocol to establish this connection. No matter what kind of internet protocol it uses, like TCP IP, named pipe, shared memory, no matter what kind of internet protocol we use, the process will remain the same. So once the SNI will secure the network connection, the query that the user is sending is wrapped inside a tabular data stream packet, which is also known as TDS packet. This particular TDS packet is given to the SQL operating system by SNI. So once the tabular data stream packet has reached at the SQL operating system, SQL OS will first identify that coming connection as a SQL connection, and it will assign a SPID to it. You know the SPID, right? SQL process ID. When you do SP-who2 or SP-who in your management studio, you see those SPIDs. SPID number 67, 94, Those are the active connections which are made to the SQL Server. So once the speed has been assigned, SQL operating system will go ahead and unwrap that tabular data stream packet. Once the TDS packet has been unwrapped, that particular query is identified as a SQL query, and that query will be now sent to the first step inside the relational engine. Now, the first component inside the first step of relational engine is parser. So the parser, it will identify and validate the syntax of the query. Like, let's say an example, like I wanted to do a select star from a table, but by mistake, I have given select star from. In that particular scenario, the parser should first identify as a syntactical error, and it should throw back me an error saying it is syntactically incorrect. And so syntax is checked here basically, and variables are declared here. Like if you are using any variables in your query, whether you are declaring them properly or not, those kind of things are checked here. And views are expanded here. For example, in your query, you are having a view, right? Behind the scenes, the query text behind that view is brought in line into the code you are sending. Basically, that view will be expanded. And with this information, the parser will it will parse and gather this information. And first thing it will do is it will go ahead and put a hash on the query you are sending to the SQL Server. It will go ahead and put a hash, and it will go ahead and check for the exact match of the hash for the execution plan inside the plan cache. So if it finds the exact hash of the execution plan inside the plan cache, it will go ahead and use the same execution plan for the execution phase. But what if it didn't find any? In that case, it will go ahead and build the initial logical tree for the first time for that query. Once it builds the initial logical tree, it will go ahead and send the query to the binder component. Once the query has now reached to the binder component, the binder component will go ahead and validate the objects, like whether your tables, columns, whether they are valid or not. Parser will just parse for the syntactical errors, but the binder is the one which will validate the objects. Binder is also known as algebraizer or normalizer. And at the binder component, check user permissions happens, like whether the user who is running the query, whether he have enough permissions to those objects or not. Those kind of things are checked here. And data type resolution also happens here. What do I mean by data type resolution, right? Let's take an example of a simple select statement between two tables, right? You are using union all clause between those two tables. So when you are using union all between those two tables, the ordinal columns of those two tables should match in their data type. If they doesn't match, then there will be an error. So those kind of things are checked at the binder component. And aggregate binding also happens here, like sum, average, those kind of things are bound here. Now with all this information, the binder component will go ahead and update the parse tree inside the plan cache. And then now our query will go to the simplification component. Simplification component itself says it will simplify something, right? So simplification will go ahead and simplify our query. Let's take an example, like if you have any subqueries in your query, no matter how many times you are running those subqueries, behind the scenes, those subqueries are converted into simple joins. And contradiction detection happens here. Like if you have any foreign key contradictions, those kind of things are detected here. Now with this information, the parse tree inside the plan cache is once again updated, and our query will go to the trivial plan component. Once the query has now reached to the trivial plan component, if our query that we are sending to the SQL Server is very simple, like an example, select star from a table or select star from a table with a very simple where clause. SQL Server will treat that query this way. This is such an easy query. Why should I even go ahead and update the parse tree inside the plan cache? Why should I even consider that? Now, all these previous components has been built a parse tree. I do not want to consider that. Let me go ahead and just discard that parse tree inside the plan cache, because now I can go ahead and build a trivial plan on the fly just like that, because it did not cost it much. It did not cost any resources to create those trivial plans. And by default, these trivial plans are not saved inside the plan cache. Now, why? There is a reason. SQL Server doesn't want to waste any cache inside the plan cache for these simple queries, right? It doesn't cost much resources to create these. It instead wanted to save the cache for the more complicated execution plans. Now, if our query is so simple, this particular trivial plan gets generated, and that plan will be now sent to the execution phase, and it will be sent to the storage engine. But what if our query is not so simple? What if our query has 10 tables in it and a complicated logic in it? Then that particular query is treated as a complicated query by the SQL Server, and it wanted to create a full plan for it. Now, whenever it thinks it is a complicated query, that query will now go to the second step of the storage relational engine, sorry. So let's think our query is complicated, right? Now let's go ahead and send that query to the second step inside the relational engine. So the first component inside the second step of relational engine is load metadata. Most of the metadata that it requires to process any queries are gathered here. Now, what are those, right? The index statistics and histograms are gathered here. Now, what are these statistics? Statistics are the blob structures which are saved inside the system table to describe the distribution of the data inside a column or set of columns or an indexed view. So basically, the optimizer will go ahead and it will get this information from the statistics and trust this information to determine how many rows it is going to think it coming out of a table or a column while we are running any queries, right? So SQL optimizer will trust this information from the histograms of the statistics. Auto create statistics also happens here. Now, let's take an example. If you are running a select query and searching on a column very frequently, and that column where you are searching on, that column, if it is not in the key columns of the index, then SQL Server will think, why should I not go ahead and create statistics on that particular column? Because now I'm frequently running these queries. It would be better for me to estimate these, how many rows does it think like it is going to come back out of that column. It will be really useful for the optimizer to grab this information from those statistics. So in that scenario, SQL Server will automatically go and create the stats on that particular column. Cardinality estimates are also gathered here. Like I said, the statistics information that the optimizer have to analyze and think how many rows does it think are going to come back out of each operator inside the execution plans. So those kind of information are gathered here. SQL Server and Windows collation are checked here, and set options are also checked. Like let's say set XML on or off. If you are using any ANSI padding, like set ANSI padding on or off, depending upon on or off setting, your execution plan might be dependent. Now with all this gathered information, the load metadata component will go ahead and update that information inside the parse tree of the plan cache. And now our query will go to the join heuristic component. Now what happens with these join heuristics? It will reorder the joins like I discussed in the previous slides, like reordering of join. But let me go ahead and explain here with a very simple example. Let's take an example of a simple select statement between 3 tables and we have 3 joins in it, right? What if the join between A to B is filtering out around 60% of the records from the result set, and the join between B to C is filtering out around 99% of the records from the result set. In that case, the optimizer will go ahead and reorder the join in such a way that it will push back the join between B to C, front of the statement, and the join between A to B, back of it. Now, why it does that is because it wanted to grab the results as quickly as possible. Now, once again, with that information, the parse tree inside the plan cache is updated, and our query will now go to the search phases. Now, I am going to discuss about the search phases in the very next slide. But for now, just remember that the optimizer is a cost-based optimizer. It always wanted to choose the good enough plan instead of the best plan, right? So it will go ahead and grab that information from these three phases, phase 0, phase 1, and phase 2. Once it grabs that execution plan information, it will go ahead and update that information inside the parse tree of the plan cache. And finally, it will put a hash on that particular query tree inside the plan cache. And now our query will go to the storage engine component, the third step. But before going into the third step, let's see what these search phases are. So no matter what kind of query we are sending to the SQL Server, the optimizer have to go ahead and get that execution plan information from these three phases. The phase 0 is also known as transaction plan. All the execution plans are created at this phase 0 are at the pre-optimization stage. That means, what is this pre-optimization stage, right? Pre-optimization stage is the first step inside the relational engine. That means the parser, binder, simplification, and the trivial plan. Those components comes under the pre-optimization stage. So that means the trivial plans are gathered here, right? They are generated here. And these execution plans are created as quickly as possible. And for the queries with maximum of 3 tables in it. And to generate these execution plans, very basic heuristics are needed, like table definition, query definition, very basic ones. But what about the phase 1? Phase 1 is known as quick plan. That means the execution plans that are generated here are also pretty much generated very quickly with maximum of 8 tables, like any queries with maximum of 8 tables in it. More transformation rules are needed than the phase 0. Now, what happens with the phase 0 and phase 1 is the optimizer, it will go ahead and compare our query with already existing execution shapes. If it finds a good enough plan, it will go ahead and grab that information. But that is not the case with the phase 2. Phase 2 is completely different. Phase 2 is known as full plan. Now, these execution plans are created for more complicated queries, and most of the parallelisms, spills, and spools to the TempDB happens here. Now, it's not like the phase 0 and phase 1. The optimizer have to now go ahead and unlock all these transformation rules, like some thousands of them, right? Now, what in the phase 2, what the optimizer does is it will just go ahead and prune off all the transformation rules it doesn't need. Now, what I mean by that, let's take an example. Let's take an example of a select statement, where we do not have like n varchar max data type, right? Now, if we are executing that particular query, optimizer will go ahead and first prune off all the transformation rules which are related to that n varchar max data type, such that it can go ahead and analyze some of the transformation rule that it needs to grab that good enough plan. That's how the optimizer will go ahead and get that information from. Now, our query is at the storage engine component, right? Let's talk about the read transaction first, like what happens. As our query is at the third step of the storage engine, no matter what kind of query we are sending, like read or the write transaction, the query should definitely pass through the first step of the relational engine and second step and come to the third step, right? But depending upon the complication, like if it is very lightweight query, which is easy for the SQL Server to go ahead and generate that trivial plan, then the query will generate the trivial plan and come to the third step. It won't touch the second step. But if the query is so complicated, then that particular query should pass the first step and then come to the second step and then to the third step. But once the query reaches to the third step, all the difference happens here at transaction manager component and the buffer manager component. Now, first, let's go and talk about the access methods for the retransaction. Access methods by itself, it doesn't perform any action, but all it does is to analyze how it have to grab the results from the disk subsystem. That's all it do. Once the query has now reached to the transaction manager, the transaction manager have two subcomponents in it, the log manager and log manager. Now, as this is a read transaction, we are not modifying any data inside the buffer pool, right? We are just reading. So transaction manager will not invoke the log manager, but it will just go ahead and invoke the log manager part of it. And it will request the buffer manager to put the shared log on the resources the buffer manager needs to process this query. Now, why shared log? Is because this is a read transaction. We are not modifying any transaction, right? So once the query is now reached at the buffer manager component, the buffer manager component, it will go ahead and first put the shared log on the resources it needs, and then go ahead and check if all the resources that it needs are already inside the buffer pool, right? Like if it didn't find some of them or all of them, it will go ahead and grab those pages in the form of 8 KB pages, put them inside the buffer pool, do the operation over there, and send the results to the user. That's how the read transaction works. Very simple. But let's go ahead and talk about the write transactions, right? Access methods by itself, it doesn't perform any action, but all it does is to analyze how it have to grab the results from the disk subsystem. Once the query has now reached to the transaction manager component, the transaction manager component, as this is a write transaction, before modifying any data pages inside the buffer pool, transaction manager has to first write those changes inside the transaction log. So transaction manager will go ahead and write those modifications inside the transaction log and then invoke the log manager part of it. It will go ahead and invoke the buffer manager to put an exclusive lock on the resources it needs to process the query. Now, why exclusive is because this is a write transaction and we do not want any operations to be interfering with our operation, right? Again, the asset properties that we have discussed earlier. So once the query has now reached to the buffer manager component will first put the exclusive lock on the resources it needs, and then it will go ahead and check if all the pages that it needs are already inside the buffer pool. If it didn't find some of them or any of them, it will just go ahead and grab that information in the form of 8 KB pages, put them back in the buffer pool, just like the read transaction, do the modification over there, and then send the success message to the user. Now, did you observe here something? The data pages has already been modified inside the buffer pool, but they are not yet hardened to the database file system. That's when the checkpoint process will get kicked in to push back these dirty pages and harden them onto the database file system. That's how the write transaction works. Now, let's go ahead and see a very quick demo of how these pre-optimization stages works, like the parser, binder, simplification, and the trivial plan component works. It's a very quick demo. I won't take much time. Let me go ahead and share my management studio. Hope you are seeing my management studio. Can you please confirm?
Yes, seeing it.
Thank you. So in this particular demo, we are using AdventureWorks 2016 database. So let me go ahead and turn on the parse only option, right? So when I turn the parse only option on, it won't it won't execute the results or it won't generate the execution plan. But all it does is it will just go ahead and parse the query. It will check whether there are any syntactical errors. Now I can do this in two ways. I can set the parse only option on, or I can even use this tab here like button, parse button inside the Management Studio. Now let me go ahead and see if this particular query have any syntactical errors. No, it doesn't. So it won't generate any errors. But here, I'm not declaring any variable, but still I'm using it in the where class. So when I execute that query, it should throw me an error saying must declare the variable, right? Now let me go ahead and do a select non-existing column from a non-existing table. Now let's go ahead and see how parser works. When I execute, it said commands completed successfully. Now why? Is because parser will only parse the query. It doesn't bind, it doesn't check whether the objects are valid or not, right? Now let me go ahead and set the parse only option off. And let me go ahead and turn on the set format only option on. Now, when I set this format only option on, both the parser as well as the binder components will kick in together. Now, when I use this option, parse only option, it doesn't execute the results or it doesn't generate any execution plan. Now, this particular set format only option is deprecated, but still I'm going to use in my demo because I can clearly show you. And until they completely remove it, we can still use it. Yes. Let me go ahead and turn this on. And let me grab this down. So this particular query, all the objects are valid and syntactically it is correct. So when I execute that, see, it doesn't produce any results, right? Now let me go ahead and run the same query one more time. Select non-existing column from a non-existing table. Now when I do that, now the binder component is also kicked in together with parser, right? It should throw me an error saying invalid object name. Now let me go ahead and set the format only option off. And let me go ahead and show you how the data type resolution occurs, right? Here we have a very simple select statement between two tables, and we are using union all clause in between those two tables. The ordinal column of these both tables should match in their data type. The customer ID here is of an integer data type, and the sales order ID is also of an integer data type here. So when I execute that, it should produce the results, right? Now, what if I manually created the data type resolution error? Customer ID here is of an integer data type, but now credit card approval code is of a varchar data type. Now that doesn't match, right? So when I execute that, it should throw me a conversion fail error. That's how the parser and binder works. Now let me go ahead and show you how the simplification component works. Let me go ahead and put the database in the context. And then simplification will simplify the query, right? So this particular simple select statement have a subquery in it. So when I execute that particular query by enabling the actual execution plan on, let me go ahead and execute that. So when I executed that, let's see the execution plan over here. Did you see here? It has actually converted that simple query behind the scenes. The subquery is converted into a simple inner join, right? That we can clearly see that in our execution plan. Now, let me go ahead and show you how the redundant joins are removed. Like simplification will also remove any redundant joins. Like here, we are only grabbing the results from the sales order header table, this table, but we are simply using the customer table here. We are not actually getting any data from the customer table. Now, when I go ahead and execute that, behind the scenes, when you see in the execution plan, it will only grab the results from the sales order header table. It did not even touch the customer table. You know why? Because we have that foreign key relationship between these two tables, the sales order header and the customer table. So SQL Server thought like, I can trust this relationship and I don't even have to touch the customer table because those two already have the foreign key relationship between them. But what if you do not have any relationship between those two tables, right? In that scenario, SQL Server should definitely go ahead and use customer table inside the execution plan to check whether those values are matching or not. Now, how does the contradiction is detected, right? Here, I'm manually creating a contradiction saying where territory ID is equal to 1 and where territory ID is not equal to 1. So when I execute that particular query, it should not produce me any results, right? Because there is a contradiction. Now let me go ahead and show you how the trivial plans are generated. This is a very simple select statement with a simple where clause. Now when I execute that query, go to the execution plan and do the properties on this particular select and go ahead and see here the optimization. There should be optimization level here. Did you see here? SQL Server thought this particular query is so simple that it did not require much resources to generate this trivial plan. It just went ahead and created the trivial plan on the fly. No matter how many times you run these kind of simple queries, behind the scenes, trivial plans get generated and those plans will not save inside the plan cache, right? But what if you are running some query and you are really expecting the SQL Server to create the full plan, but it's just going ahead and creating the trivial plan, right? We do not want to mess with that, but there is an option like where you can save that trivial plan, right? If you wanted a full plan, there is no option to save that full plan inside the plan cache except to convert that full trivial plan into a full plan so that it can be saved inside the plan cache. So by enabling this trace flag 8757 inside the query, when you mention that inside the query, it is only bound to that query. It doesn't affect the server level or the database level. So when you execute with that trace flag on, SQL Server will just go ahead and convert the same execution plan. There is no change in the execution plan. But then if you do the properties, it will just go ahead and convert that plan into a full plan. That means this particular plan is now saved inside the plan cache. I really do not suggest you to do this in production because there is a reason why SQL Server doesn't want to save this inside the plan cache, right? Because it wanted to save for the more complicated execution plans. But yeah, you have an option here. So that's how the trivial plan components and the simplification component works. So let me go ahead and very quickly share back my slides. So in the summary of this particular session, we have mainly focused on, like, we started with the basics, the asset properties, with a very simple example, ensuring the asset properties of transaction. And now each and every relational engine transaction should ensure this asset property. We have gone through the overview of what type of components we have inside the memory architecture of SQL Server. In this particular session, we mainly focused on plan cache and buffer pool because those are the bigger components. And we have seen the life cycle of a query for the read as well as the write transactions, like what happens behind the scenes at each step inside the relational engine. And we have also gone through the components of the SQL engine. That's the components of the relational engine and the components of the storage engine. So in order for me to prepare for this presentation, I have followed several resources, but these are the main ones. So if you wanted to learn more about internals, please follow these resources. And I would like to thank DenverSQL user group for giving me this wonderful opportunity to present for your user group. It's an honor. So if I get a chance, I will be back again soon with a very new topic. So thank you so much once again for attending this session.
Thank you, Deepthi. Mark had to step away for a moment, but just wanted to say thank you very much. Do we have any questions from anybody? All right. I'm not hearing any questions. I'm seeing a lot of thank yous on the chat, however.
Thank you for attending.
That was wonderful, very in-depth. I'm going to go ahead and hit stop on the record.
Sure.